Okay, good. Okay, so now, we know how to implement. The point is, how do you implement this physically? So this is almost the last topic of this class, right? Next year, I'm not going to teach you. I will move everything to 274. How do we implement this one? So let's really look at a physical system, the spin qubit, okay? Before that, it would be good to go over some of the physics. Just take it for granted, but it's good to review a little bit, right? There are a few concepts I want to talk about. If you have a circle, a wire, and then the electron is moving around, right? Instead of electron, I just say a current is moving around I. And if this is an area A, okay, the circle area A, and we know that even area has a direction, right? For those who talk E140, area has a vector, right? And it depends on where you call it. Anyway, the direction is perpendicular to the area, and the magnitude is the area, okay? If your current moving in this circle, you are going to create something called magnetic moment. And trust me, this is just physics. They say so, we believe so. Current create a magnetic moment, okay? You know it create magnetic field, and this magnetic field associated with a magnetic moment. That's it, right? Moment equals to I times A, okay? Whatever you have. Right now, of course, we always have something simple. We don't need to worry about the vector most of the time because ours is something very simple. Then just the value of the magnetic moment, mu, is just I times A, right? In scalar form. A is what? Pi r squared, right? And what is I? Well, I is delta Q divided by delta T, right? Basically, is that for unit time, how much charge pass through, okay? So this delta Q is contributed by one electron. So I say negative E, okay? Here I have E equal to negative 1.6 times 10 to the power negative 19 Coulomb, okay? So E is negative in this notation, okay? So I make negative E because that is I, how much electron going through, right? How much current unit charge. And what is T? T is basically how long do I pass through a point? It's equal to the velocity, to the length, the electron travel, which is 2 pi r, divided by its velocity, right? That is the time you go through one circle. So for so much time you go through one circle, so that this unit of time I have one electron, then this is the current, okay? So if this is the case, then the mu is just equal to I negative E times V divided by 2 pi r. I need to emphasize this V is velocity, not voltage, times R times pi r squared, which is the area, right? Right? And then R got cancelled, pi got cancelled. You basically get negative E V R divided by 2. Am I right? Yes, right? Now, in physics, we have something more fundamental. We want to go to that quantity. So angular momentum is something we want to use. Velocity is not a canonical variable that we want to use. Just like earlier we talked about the simple harmonic oscillator, right? We use linear momentum versus position instead of mv squared, p squared over m. Right? So the angular momentum of a rotating object is mvr, okay? So this one, you trust me, if you remember, this is the origin, and this is R, and this is V, then the angular momentum is just R cross product V times M, but because they're at 90 degrees, so just MVR, right? The way we do this, because I want to show you that the mu, then if I substitute into it, it's just equal to E times L divided by M, or by 2M, right? Or mu equals to negative E divided by 2m times L, right? So after all this, I just want you to have a feeling of how we get this equation. You don't need to know that. The most important is that the magnetic moment is related to the angular momentum. This is magnetic moment. This is angular momentum by a fraction, but by a number. This number is so-called gyromagnetic ratio. Okay? It's just saying that if you have a charged particle, which you have this type of angular momentum, you will create the corresponding magnetic moment. And even for this line, maybe it's not that important. But I want to share with you. I want you to know about this so when you read more, you understand what people are talking about. Okay, so in summary, if this charged particle have this magnetic angular moment, this charged particle has this angular momentum, for electron, then it has a negative up direction of magnetic moment. Okay? If its angular momentum is pointing up, its magnetic moment is pointing down. Why I want to say this? Maybe I don't need to say this. But then we can even directly go to the spin, right? Now, what I'm talking about is just an object you really see is rotating. It's at an angular momentum. This is perfectly classical, right? You and I can get the angular momentum. And I'm not charged, so I don't have magnetic moment. If I positive charge, then my magnetic moment is the same as my angular momentum. If I negatively charge, my magnetic moment is in opposite direction to my angular momentum. That's what I want you to know. And they have a very important number, gyromagnetic ratio, which makes sense because angular momentum is related to your mass, and magnetic moment is related to your charge. So probably it's the charge divided by the mass, right? But you have a factor of 2. Spin is something like the rotation, but it is not a rotation, right? Because spin resides in a space we don't know. It's just a character of the particle, another nice quantum number. You can say this one has this angular momentum, but it has something called spin. I feel it's easier to appreciate if we even talk about the color charge, the quark. Quark, they have red, green, blue. If I'm correct, I think it's red, green, blue. Of course, they don't have color. It doesn't mean that they have a color, red, color, green, right? Because they are much smaller than the wavelength. You can never see their color. That is just a property. And they can exhibit an energy under certain external. For example, if you have a spin, you also cannot distinguish your energy until I put a magnetic field there, right? But you don't have that property. It's just like if you're a boy, you're a girl, maybe, let's say your voice is different. If I don't hear your voice, I cannot distinguish whether you're a boy or girl until I talk to you. That is like that, right? Of course, that's not a perfect analogy. The spin is just a character. But however, it looks like the angular motion. It looks like a ball is spinning. But no, electron is not spinning. Electron is not spinning. It is a point charge. It's a point particle. It has no dimension. Right? So it's not spinning if it has no dimension. But its property looks like the angular, looks like a rotation, right? So what I'm going to give you are all given again, right? We are not going to prove, and I think we cannot prove it for spin. It's just a property. So an electron has something called spin quantum number. Okay? It can be plus or minus half. That's it. The physicists tell us that. You trust that. Right? Just like you can be positive or negative charge. right? Here you plus or negative or half, plus or minus half. That is the spin. And associated with each spin, you do have the angular momentum. You are not really rotating, but because you have the spin property, you have the angular momentum, which is equal to plus minus h bar times the spin. H bar times the spin. So this one will confuse you actually. Should I say that? Just call it times the spin, but the angular momentum is s. Okay, this plus minus 2 is the spin quantum number, right? So you spin half, then your angular momentum is h bar divided by 2. You spin negative half, your angular momentum is negative 1 over 2. Just the property, right? Are you going to feel it? You basically don't feel it, right? You say you have angular momentum. I don't see it because I cannot touch the electron. It's not really spinning. Until what? Until because it has an angular momentum, it also has a spin magnetic moment. So if the classical object is rotating, it's really rotating, it has an angular momentum, and now I tell you that this spin, although it's not classical, but it's the same, it also has an angular momentum. But just do not think that it's really rotating, but it does have this angular momentum. It just has this angular momentum. So it then also has a corresponding magnetic moment. And once you have magnetic moment, I apply a magnetic field, then I will see the energy difference, then I will know that where is your magnetic moment, and then I know what is your angular momentum, and then I know whether you spin up or spin down. Do you see what I mean? Right? Just like a classical object, let's say I cannot see it moving, all I need to do is just to measure its magnetic moment, then I will know that whether it's rotating clockwise or counterclockwise. This is the same for spin, except that we need to remind ourselves the spin is not really something rotating, but it has the angular momentum, which is called the spin angular momentum. But what is the ratio between the spin angular momentum? Let me just remind you, right? The classical one, I just told you, the classical one is magnetic moment equal to E divided by qm times L. Yes, thank you. Right? If I use the classical one, then what should I get? I should get plus minus E divided by 2m times 1 over 2h bar, right? If classical. If I use the classical way, make sense? Because the L, which is here, right? So now L become S plus minus h bar, right? But this is wrong. Exactly. It's analog to only analog, right? It turned out it is wrong. The real one is what? It turned out it is mu approximately equal to E divided by N h bar divided by 2. It's about 2x larger gyromagnetic ratio. Okay, so because of this, we will write it as mu E equals to negative G times mu B S divided by h bar, right? So what is mu B? Mu B is the so-called Bohr's Magneton, EH bar divided by 2m. Okay, so if you substitute this to here, you will see that indeed this is correct with G approximately equal to 2. Okay, so I don't need you to be familiar with this equation. In assignment, I think I asked you to do something, to do some calculation. But you don't need to be familiar with this. The main point is that you understand the gyromagnetic ratio in the spin is about 2x larger than the classical one. And you even don't need it here. The main point is this is a very important number. It's not 2, it's 2.02 or something. And people still finding it because this is related to the Feynman diagram. And eventually, I remember in a seminar, if they can calculate it well, it's related to the dark matter of the universe. So very interesting. This is very deep physics, right? I don't understand. But if you calculate it and its value is going to tell you whether how much dark matter or whether it's dark matter in the universe, because it's related to very fundamental physics. Okay? But for us, I give you this just as a story. But the most important thing you need to remember is spin has a quantum number, then it has an angular momentum, plus minus h bar. And then it has a magnetic moment. And this magnetic moment can be represented as this equation. And you just remember that it's 2x larger than if you were using the classical one. But you never need to do that, right? You just know that it's equal to this equation, and that's it. Is that okay? Now, so to be frank, even up to now, I would like you to understand this, but not that important. Up to now, I just give you a background. Eventually, you just know that electron has spin and it has magnetic moment. And because it's negative charge, so its magnetic moment is opposite to its spin. Okay? Because its gyromagnetic ratio is negative. Photon is different. This affects how we look at the broad sphere. Now, this is like what happened. If I have the magnetic field pointing down, okay? Or it doesn't matter, just make it pointing down. And then I have a magnetic moment of an electron. Then it will create an energy. This energy, Hamiltonian, is equal to negative magnetic moment dot product with the magnetic field. Okay? Again, why is this? Given. Okay, I actually don't know how they prove this. Maybe just experimental observation. If you align, if the magnetic field is pointing up, the magnetic moment is pointing up, what happened to the spin for electron? Is pointing up or down? Pointing down because it's opposite, right? You actually have H positive or negative? H equal to minus mu dot B, and mu and B are both pointing up, so it is negative or positive? Negative, right? Because you're pointing in the same direction. The dot product cosine 0 equal to 1, right? So this is smaller than 0. It means I have lower energy. If magnetic field is pointing up, but the magnetic moment is pointing down, it means the spin is what for electron? Pointing up. So you have lower or higher energy? You have higher energy because magnetic field and magnetic moment are pointing in opposite direction, so their angle is 180. Cosine 180 is negative 1, right? Because what is this? This is just equal to mu B cosine theta, where theta is the angle between them, right? These are two vectors, right? So it's positive. So basically, this is what I want to say. You have energy. You have a spin up. You have spin down. When the magnetic field is equal to 0, they are the same. They have the same energy. You cannot distinguish them. Okay, so don't tell me you are spin up, spin down. You tell me you're good, you're bad in study. I have not tested you. I don't know. You are the same, right? And how do I test you? I'm going to apply a magnetic field. And in this case, apply the magnetic field down. Okay? When I apply the magnetic field down, this is a little bit opposite, right? If it's applied down, then which one will give me lower energy? Apply it down, then then it means the down magnetic moment will have lower energy, right? But then it means spin up will have a lower energy. Okay?
So essentially by applying the magnetic field, you're splitting the energy.
Splitting of energy. Exactly. That is so-called Zeeman effect, right? But we even don't want to talk about this physics term. Yeah. So then the one that have the magnetic moment pointing up, which is opposite to magnetic field, then it means the spin is pointing down, actually has high energy. What is the difference between these two energy? Each of them gain how much? Right? Reduced by mu b, right? Each of this, right? For the spin down, you reduce by negative mu b. Spin up, you increase by mu b. So the distance becomes 2 mu b. The magnetic moment times the external magnetic field.
So the stronger the
Exactly. Larger, stronger magnetic field, the gap will be larger, which makes sense, right? Because when the magnetic field is 0, I cannot distinguish them. That is how you find out the spin. Now, eventually, right, we keep saying spin, up, down, 0, 1. Now, is that you need to apply the magnetic field to measure their energy. Okay, good. Now, if I want to see how it evolved, I need to construct the Hamiltonian for this system. I already know what it is. I already know this is H equals to negative mu B0, right? Now I will just make it the this one. Now, how do I construct the Hamiltonian? First of all, I'm going to call spin up as 0 state. Okay, spin down as 1 state. Okay. This, let's see. How do we construct it? We remember all the matrix can be constructed by using their eigenvalue. 0 to 1, lambda 1, I. Do you remember this? Probably you forgot, right? Because every matrix can be constructed with its eigenvalue in the diagonal basis by using the corresponding eigenvector, right? If you forgot, go back to take a look. But what is the eigenvalue of this matrix? This is the Hamiltonian, the energy, right? It only has 2. Yeah, it is what? When, let's do it. Yeah, it had 2 states, right? Let's do it. Let me write it out. It's like this. Right? When it is the 0 state, its eigenvalue is lambda 0. When it's 1 state, eigenvalue is lambda 1. When 0 state, which is spin up, what is its eigenvalue? No. What is this eigenvalue? Look at this. What is the energy that I apply when it is a 0 state? What energy does it get? Negative mu B0, right? When it is down state, it is mu B0, correct? That is the energy it gains when we apply the magnetic field, right? The whole system, it is at 0 state. When it is pointing up, when it is up state, apply the magnetic field, then the energy becomes negative mu B0. It is pointing down, the energy becomes mu B0. So that is the energy that it has for this whole system for these two states, right? So as a result, this is equal to negative mu B0 1 0 0 0 0 plus mu B0 0 0 0 1. You just do the outer product, which gives me negative, the mu, I let you give you, I also kind of lost. This is mu. Look at this one. The mu is equal to 2 times the Bohr magneton, so this got cancelled. Or just look at this, EH bar divided by 2m. EH bar divided by 2m is the mu, okay? So I have EH bar divided by 2m times B0, 1 0 0 0 plus EH bar divided by 2m, B0, 0 0 0 1, which is equals to negative EH bar divided by 2m B0, 1 0 0 negative 1. And that's what you said is Z gate again. And indeed, I'm trying to implement the Z gate, right? This is equal to negative HZ sigma Z, where HZ equal to EH bar divided by 2m B0. Okay? So because of time, stop here. But the point is that we have constructed the Hamiltonian by using a physical system. The system is what? I apply a magnetic field in the Z direction with the right energy. And then I'm using the spin property of the electron through the interaction between the magnetic moment and the external magnetic field to construct this Hamiltonian. And now you can see that after that, I can start manipulating the qubit. Yeah. Oh, it's related to quantum annealing because these sigma Z gates, they are all there for quantum annealing. But this is not just quantum annealing. This is just a gate, right? I can, just a manipulation of the qubit through the magnetic field. And this is under control. But you can use it for quantum annealing, of course, yeah.